Good morning, dear students. Last session we have talked about shrinkage in concrete. And, I'll just run through the slides. What happened in the last session? So, shrinkage of concrete is due to contraction due to loss of moisture, and this is by two ways. Uh, One is loss of water from voids, what we call drying shrinkage, and the other one is reduction of volume during carbonation, which means the amount of water used for the chemical reaction. That's how you use the reduction in volume. That is called autogenous shrinkage. This is what we discussed in the last session, and also the factors which try increase the shrinkage and which decrease the shrinkage talked about. And also how to estimate the shrinkage of concrete. The codal provisions clearly mentioned in clause 6.2.4 will give you the complete detailed ready-made formulas, also the tabular values of these two different shrinkage values to calculate. Okay, this is what we have talked about in the last session. Right. Next, going to the another property of the prestressed concrete, which is high strength concrete, called creep. Okay. Right. So, what is meant by a creep? Okay. So, creep is defined as increase in deformation with time under constant load. Okay. So this is what is the definition for creep of concrete. Increase in deformation means development of strain. Okay, under sustained load, right? Which means constant load, almost constant load. Okay, because once the structure is constructed, for some of the structures, the dead load and live load is almost constant throughout its lifetime, unless you change the occupancy, the purpose of the structure, then only it will change. Otherwise, the loads are almost constant on the structure. Okay, so something like a building is constructed. For example, an educational building is converted to a community hall, something like that. So the intended purpose, if you change, you can expect the change in load, right? Right. Due to the creep of concrete, the pre-stress in tendon is reduced. Okay, with the time. The reason behind that, as you have the uh, deformation, increase in deformation with the time in the concrete, the pre-stress is reduced. Okay, that is what is called loss of pre-stress due to creep. Okay, creep of concrete. So we have a detailed estimate for this, how to calculate the loss in pre-stress due to creep. Okay, right. This creep property of concrete is due to two causes. One is the rearrangement of hydrated cement paste, especially the layered products. Okay, This is one such aspect. And expulsion of water from voids under the load. Okay. So this is another reason. So there are two reasons for creep to occur. One reason is the rearrangement of hydrated cement paste. So once the cement concrete is prepared, the cement paste is going to move around the aggregate particles, aggregates to when you load it. It is rearrangement of hydrated cement paste. And expulsion of water from voids when you apply the load on the concrete, the volume tries to reduce so that the water from voids tries to escape. Okay, that is expulsion of water from voids. So these two are the reasons for it. If a concrete specimen is subjected to slow compressive loading, I mean the application of load depending on the time variance. Okay, so that is important. So the stress versus strain curve is elongated along the strain axis as compared to the curve for fast loading. Okay, so the pattern of loading is also influencing the creep property of the concrete. So that is by something like this. You can explain like this. If the load is sustained at a level, a particular level, means if you keep the load constant, the increase in strain due to creep will lead to the shift from fast loading curve to the slow loading curve. Okay, the stress strain diagram will be shifted when you take the load at a particular level. That if you see in the diagram, it is very clear. So there are two curves that you see it here. Strain on x-axis and stress on y-axis, just to study the creep property. So if any member, concrete member, is loaded at a faster rate, the stress strain diagram will follow this line. And if you change the rate of loading to a lower level, slow, when you slow down the rate of loading, for example, 100 newtons per minute, 200 newtons per minute, something like that. So if you slow down the rate of loading, that this testing is very simple. You can do it in your uh, the testing machine in the laboratory, where you can fix the rate of loading. Okay, how much load to apply per minute or so. So if you slow down the loading, the same concrete is behaving like this. Stress strain diagram will take a different path. Same member, same concrete, just the rate of loading is changed. Faster rating, slower rating. Means if you want to apply say 100 kilonewton load, so you start from 0, then 1, 2, 3 like that. We go to 100 kilonewton to reach. The point here is to apply from 0 to 100 kilonewton load. How much time you are taking? Okay, if you take just uh, within 5 minutes, within a time period of 5 minutes or 10 minutes, if you reach from 0 to 100, that is one sort of load. If you take 1 hour for loading from 0 to 100 kilonewton, that is slower rate. That is what I mean, the rate of loading, the amount of load that you apply per unit time. Okay. So such case is the fast loading and slow loading. Okay. So that's how you see. Now you take a level of loading. So for example, this is the stress level. You can see the effect of uh, rate of loading is this much. Means what happens? The strain value for the same stress is different. Okay, so this is less value, this is more strain is developed. This less strain is developed. What is this effect? This is what is called creep. Okay, right? The property of concrete called creep is because of the sustained loading. If you keep the load for the longer duration, the additional amount of strain that you get is called creep. Okay, right. So that's about the rate of loading also is having the effect on concrete deformation. Okay. So definition itself is like that: increase in deformation with time under constant loading. Okay, right. Creep is quantified in terms of strain. A creep is a property that you have to measure. So we measure in terms of strain, right? How do you express the creep property? Is by strain value. Okay, that occurs in addition to the elastic strain due to the loads. Normally, when you apply the load, concrete member deforms. That you call elastic strain. Okay, if you keep the same load for some time, we apply load uh, on the concrete, we get strain. Okay, if you keep that load for 1 month, 6 months, for 1 year, the strain is going to increase even you don't increase the stress value. Generally, if you increase the stress, the strain has to be increased. Right? That's a prime concern for us. Right? Even though you don't increase the stress value, means keep the same load for some time, then you find the strain is increasing. That is what is called, the property is called creep. Okay. So that value you have to mention in terms of strain, right? If the applied loads are close to service loads, the creep strain increases at a decreasing rate with time. Okay, that is mentioned, represented in terms of diagram that we will see. If the load is close to the service loads, okay, the ultimate creep strain is found to be proportional to the elastic strain. Okay. So always the ultimate creep strain is proportional to the elastic strain. That's why the quantification of creep strain is easy. So that is by the nature called creep coefficient, ratio of ultimate creep strain to the elastic strain, which we define it as creep coefficient. Okay, so this is the property for we use for quantification of creep of concrete. Okay. Creep is a property of concrete where if you keep the load for so long time onto the concrete, it is going to deform. Okay, it is going to produce strain. That property is creep. How do you say in terms of a value, in terms of a number? That is by the property called by the definition creep coefficient, that is theta. Okay, so creep coefficient is the ratio of ultimate creep strain to elastic creep strain. Okay, the creep coefficient theta definition is like this. Okay, so it is always going to be more than 1 point something. 1.0 is the least value. 1.0, okay, is the least value. Beyond that, 1.1, 1.5. Likewise, it can be any value more than 1. Right. The variation of strain with the time under constant axial compressive stress is represented here. So x-axis we draw time, y-axis strain value. So when you apply the load, for example, we cast a concrete member. For example, a beam is casted and erected, and it is after 28 days it starts taking the load, right? Okay, it starts taking its self weight itself. Maybe after 6 months of the construction, you move in to the structure along with your furniture and people. Likewise, all live load things will come into picture. Until unless you occupy that, it will have only dead load. Once you occupy the structure, the live load starts picking up. So say this is the point where, say, a structure is constructed. After 6 months you have occupied. Now starts the load is applied. Immediately after application of load, this is the value of strain. Okay, once you start using the structure, immediately after applying the load, then as time progresses, this is the starting point of the occupancy where load is applied. Okay, immediately some strain has developed, and after that 1 year, 2 years, 3 years, 4 years, 5 years, like that time progresses, but the strain don't stop developing, because if you think that load is applied, the member is bent, elongated, contracted, something like this. uh, After load application, everything is done. You just can't take it like that. Okay, the strain won't stop developing. So the strain starts developing, and after maybe some time, okay, it it is going to, the change is going to be very minimum. And even after so many years of time, maybe after 1 day or 7 days, 28 days, 1 year, likewise, that value is going to be constant value. There won't be any change for it. Okay, so initial period is very crucial. If you see that till this point almost, okay, the this line is going to become parallel to this after this point. Okay, something like this. So this part is very crucial, where strain is developing very high. After that it is decreased. Okay, right. So that is what is called the effect of creep. So what is the final strain in the member? It is elastic strain plus the creep strain. Okay, so this is a maximum value of strain, right? Total. What is the value of creep strain? Only this value. This is elastic strain. Okay, so creep coefficient is the one which you have to remember. Ultimate creep strain divided by elastic strain. Okay, right. Now, if the load is removed, the elastic strain will be recovered. The name itself is elastic. So when you remove the load, the strain will vanish. Okay. However, the recovered elastic strain is less than the initial strain. Okay, as the elastic modulus increases with age. There is reduction of strain due to creep recovery, which is less than the creep strain. Okay, so that's why there is some residual strain which cannot be recovered. Okay, right? So uh, this is continuity to the earlier diagram. So till this point, the diagram has come. Now you start unloading. Okay, remove the load. So immediately within the elastic range, it starts recovering the strain recovery, elastic recovery. Then slowly there will be recovery, which is called creep. And there will be some strain which uh, stay in the member. That is what is called residual strain. Okay, so there will be uh, only very small value of strain recovery is there, and you can see the large portion of residual strain present in the member. Okay, right? So there will be elastic recovery and also creep strain also recovery. There will be residual strain remaining. Residual in the sense remaining value. Okay, right. Now, on what factors the creep depends on, right? So, the similar factors that we studied earlier for shrinkage, same holds good, almost similar. Cement content, water cement ratio, air entrainment, ambient temperature. Okay, so these will increase the creep value, creep strain, and decreasing creep strain. Decreasing parameters are age of concrete at time of loading. Means if you delay the loading, creep strain will be reduced. Humidity, okay, if you increase the humidity, creep strain will be reduced. Volume to surface area ratio, okay, and type of aggregates. Same, very similar properties as that of earlier. Shrinkage, okay, right. This is a table taken from IS code. You can open your IS code and see section 625 that will give you this IS code to estimate ultimate creep strain value. Okay, so this table gives you can see till 1 year of time. So after 1 year, uh, it is going to be uh, almost uh, same value as we have seen the diagram, where it starts from day 1 of loading, okay, and day 7, day 28, and day 90, and day 365. So for which you have been given the creep coefficients, okay, creep coefficient value. I said it is 1 is the minimum value that you can see it here. Okay, it is expressed in terms of a ratio of ultimate creep strain to elastic creep strain. Okay, so creep coefficient phi, okay, which is mentioned in code as phi naught. Okay, for an ordinary structural concrete after 70 years of loading. Okay, so that those are being given here, and they are being given in terms of a ratio. Okay, the number under 50% of relative humidity. These are the values for the notional size which we have discussed in the shrinkage chapter. I mean shrinkage topic. Even for relative humidity 80% also the values are being given. Now, if you just for a case, if you can see column number 6, okay, for a humidity 80%, okay, what will be creep coefficient value? Okay, for 7 days, 28 days, and 1 year. Okay, so these are the values 1.1, 1.8, and 2.4. Right, so as we have seen the curve like this, okay, so I mean, day 7, day 1, okay, the ratio is 3.4, day 7, 2.4, something like this. So this is say one line 1. So it is going to reach the line maybe very nearer to 1 after 365 days. Okay, for example, like this. So 1 day to 365 days, if you can draw this diagram in terms of ratio. Okay, so that is going to be the uh, the importance of these values, right? So I just explained here. Column number 6, if you take for 7 days, creep coefficient is 2.4. That means creep strain value is 2.4 times the elastic strain, because it is a ratio, right? Theta is equal to uh, ultimate creep strain to elastic creep strain. Okay, C. Right. So ultimate creep strain value is equal to the number that is given in the table multiplied by elastic strain. So 2.4 times the elastic strain. So almost the total strain is more than thrice the elastic strain. 3.4 times total value. I'm talking about total value. Okay. Uh, Hence, it is necessary to study the effect of creep in loss of prestress. Okay, because the strain value is almost becoming 3 times the total strain value. So, if you lose the pre-stress much higher value, the effectiveness of pre-stress is lost. Okay, that is what is the problem. Okay. So if the structure is loaded at 28 days, the creep strain is substantial. I mean the higher loss of pre-stress and higher deflection. Okay? So delay the loading, delay the application of load onto the concrete. Okay, right? So curing the concrete adequately, delaying the load application will provide long-term benefits with durability, loss of pre-stress, and deflection. Okay, so this is regarding the creep value, which the parameters influencing it, what is creep coefficient, what is a creep, right? All that, right? We'll discuss in detail in the next session the codal provisions, how the creep coefficient is calculated, right?